don't need knowledge in unsteady aerodynamics. The lift builds on the airfoil in an unsteady fashion, of course. This is the very definition of an unsteady aerodynamics, okay? Okay, so this is descriptively. This is what is unsteady aerodynamics. Any question about that? Any question, please? If you have any question, just, it's more of, this course will be more of a discussion. We're gonna build our momentum step by step. So please feel free to talk to me anytime and ask questions. Okay, so this is descriptively. What about mathematically? So I will make like this. I'll say number 2. Mathematically. We all know that the lift coefficient equals 2 pi alpha is for a pure steady flow. So this is, of course, is not an unsteady relation. This relation cannot describe an unsteady flow, right? I'll ask you one question. So can this relation, maybe 2 pi alpha minus alpha cube over 6, it's nonlinear in alpha, or any function that is nonlinear in alpha, any function that is nonlinear in alpha, maybe sine 2 alpha, or exponential alpha, any nonlinear function of alpha, do you think that this can describe an unsteady flow? Anybody agrees that this may describe an unsteady flow? So CL as a function of time is 2 pi alpha at this time minus alpha cube at this time. Can this relation can this relation represent an unsteady flow? Who agrees? Who doesn't agree? Yeah, it does not describe an unsteady flow because of the following. Like I said, no matter how you change the condition, the lift cannot respond instantaneously. What does this equation tell you? It tells you that give me your alpha at this particular time, you get lift at the same instant of time, correct? So it cannot represent an unsteady flow. So I don't need to go very deep and analyze the equation. If somebody is proposing a formula like this to represent an unsteady phenomenon, I will reject it from the get-go, okay? So what about this thing? So CL as a function of time is 2 pi alpha as a function of time plus alpha dot as a function of time, C over 2u infinity, or whatever. Some form that is function, maybe any nonlinear function of alpha and alpha dot, and you can also add alpha double dot. So alpha and its derivatives. Do you agree that this can describe an unsteady phenomenon? Who agrees? Who doesn't agree? This is a little bit confusing, but again, apply the same principle. You change the conditions, you give your airfoil not only a change in the angle of attack, but changing the angular velocity, I don't care. It's still, your change at this time dictates an instantaneous change in the lift at the same time instant. This again is not an unsteady moment. And this is really confusing. Many people in proposals, when we go to the NSF or whatever and review proposals and papers, they get the response from the Navier-Stokes equations and they try to fit the data of Navier-Stokes equations with some mathematical model that represents unsteady aerodynamics, and they propose formula like these. This one cannot represent an unsteady flow, okay? Why? Because you cannot dictate your lift. So then, how can you ever represent an unsteady flow? Mathematically, remember we're talking about what is unsteady aerodynamics, you already described it, and now we're talking how can I represent it mathematically, okay? Any idea? Any suggestion?
Some integration or something?
Some integration, that's very good. Can you flip it and give it to me the other way around? It's exactly integration, that's right, that's exactly right. But there is a well-known type of equation that we we can name for this kind of thing. It cannot be an algebraic equation. These are algebraic equations. You give me the angle of attack at this time, or alpha dot or alpha double dot. I plug them into an algebraic expression. I get the instantaneous lift. It cannot be an algebraic equation because it will dictate an instantaneous response of the lift. It has to be a differential equation, right? Any dynamical system that possesses some lag, some dynamics, is described by differential equation. This is what we learned, right? So a true unsteady model has to be represented by differential equation. Like, for example, any one, maybe the simplest one, first order. So CL dot, the dot is here. D by dt for CL as a function of time is any function, maybe 2 pi, whatever. 2 pi, or let's do it like this, maybe negative 3 CL as a function of time plus 2 pi alpha as a function of time. Now, your alpha at this time does not produce CL, but a time rate of change of CL, so that if it's maintained for a few seconds, in the next 2 seconds, it will create a change in the lift coefficient. You see what I'm saying? Okay? If you have a question, please come up with it. Okay? We're just discussing together. Yes, please.
Well, I've seen unsteady aerodynamic models like Theodorfen's
Yep.
theory.
Yeah, we'll get to that. You're right. It's not. So what I'm trying to say is that it cannot be an algebraic equation. Okay? But it has to have some form of dynamics. One way of representing dynamical systems is differential equation. And the very next thing is that to exactly say what are the different forms to represent a dynamical system. Okay? Tudorson is one of them, and Tudorson is a frequency response. We're going to get to that in a minute. Joseph, please.
Can we say anything about if the system has memory, or how?
This is great. Again, this will be a differential equation, but will be a delayed differential equation in the following sense. It doesn't depend on this alpha only, but maybe alpha in the previous time. So you will add maybe a term here that is 5 alpha of t minus 5 seconds, or alpha of t minus tau. It has a memory effect. This is the memory. It is represented by a delayed differential equation. Okay? Any question? Which is, if you remember the 170 course, the delay in the S domain is just e to the negative ts, or e to the negative tau s. And this leads us to the following. Please, if you guys need to review the 170 concepts, not all the 170, I just need the step response and the frequency response. Very essential. And from the 136, I need the flow around the circular symmetry. We will not be able to continue in this course without these concepts. Okay? So the conclusion here, the main message is that here is how we view unsteady aerodynamics. Your input is the airfoil motion, right? Your output is what? What's your output?
Lift.
Yeah, the aerodynamic loads or the lift. So I'll say the loads. Previously, this was simply an algebraic equation, whether it's linear or not, but it was actually linear, 2 pi times alpha. You plug in alpha, multiply by 2 pi, get the lift. If it's in the stall regime, but still steady, it will not be simply 2 pi times alpha, will be some nonlinear relation with alpha. Maybe you may have some alpha cube or whatever. But now we're viewing it from this unsteady perspective, we're viewing it as a dynamical system. Okay? So this 2 pi is no longer valid. Okay? It cannot be an algebraic relation, you just multiply by a gain. No, it has a dynamical nature. Which leads to the following. How to represent a dynamical system? How do you represent a dynamical system? Can you tell me one form of representing a dynamical system? What is one form? If you are in 170 and they're giving you a system, here is a system. What do they give you? Transfer function. Very good. So this is so transfer function. So we were trying to develop, when we're saying We want to develop an unsteady model. We want to develop a transfer function, a dynamical system. Okay? Transfer function that represents the dynamics of the flow from your input airfoil motion to your output, the lift variation. I'm just reminding you that the transfer function, by definition, G of S, is the output in the Laplace domain divided by the input in the Laplace domain at zero initial conditions. Usually we denote the output by Y and the input by U. So for us here, for example, if we have CL dot is negative 3 CL plus 2 pi alpha, I can immediately convert this in a transfer function model, right? Just take the Laplace transform at zero initial condition. This is very easy. The Laplace transform at zero initial condition is the easiest. It's just convert any dot to S. So S times CL is negative 3 CL plus 2 pi alpha. And this is the role of the Laplace transform, is to convert a differential equation. In the black line, by the way, I'll save this as a PDF and upload it, so you don't need to, And if you are not registering for the course, you can send me your email and I will add you to the email list and send this stuff to you. So you don't need to write, but it's up to you. You can write, not to be bored of the class. So this black line, CL dot and CL are different entities. You cannot add them together. This guy is different from that guy. But here, the Laplace transform, like any integral transform, Fourier transform, whatever, they convert a differential equation into an algebraic equation. These two